Hello, calculus students. This lesson is on basic derivative rules. Now that we have talked about how to find the derivative of a function using a limit as h goes to 0, we are going to generalize some of our results to come up with shortcut rules for more quickly finding the derivative of a given function. On this page, we want to come up with a rule for how to differentiate a constant function, then how to differentiate a linear function. And we will use the limit definition of derivative to find these generalized derivatives. Let me begin with the second one. We have mx plus b. Remember, this derivative will be with respect to x, so we assume x is the independent variable, and I'll assume the m and the b are constants. So I'll put a prime sign here as another way to indicate derivative, and this will be the limit as h goes to 0 of f of x plus h minus f of x all over h. For this part of our formula, we look at the rule of the function, and everywhere you see an x, you replace with an x plus h. So you would have an m times parentheses x plus h, and then plus the b, and then minus, and then parentheses, and then f of x is simply mx plus b, all over h. I'll do some distribution. So mx plus mh plus b minus mx minus b, all over h. Notice mx and negative mx will cancel, and so will b and negative b, leaving me a simple limit of mh over h. I can't plug in h equals 0 yet, but I can cancel h over h, leaving 1. So we have the limit as h goes to 0 of just m, and m is constant, so we get a result of m. Thus, the derivative of mx plus b, where m and b are constants and x is the independent variable, will simply give you the slope of that line, m. This will be a shortcut that we can use moving forward, so I don't have to go through this whole process every time. This also makes sense. If you imagine a function that's already a line, and then you pick different x-coordinates and ask what is the slope of the tangent line, well, the tangent line will be equal to this line, so the slope of the tangent line will be the slope of this line. And that would be true no matter which point on this curve you focused on. All the slopes of the tangent lines are simply the slope of the given line, so the derivative function of a line is simply its slope. With that thinking in mind, if you imagine a function that's a constant, when you graph a constant function, you get a horizontal line. If you pick any point on a horizontal line and then draw a tangent line, you'll get the same line, and the slope of that line would be 0. That would be true no matter which point on this horizontal line you focused on. So this tells me that the derivative of a constant ought to be 0. Let's confirm this real fast. If you have a constant and you take the derivative, you'll do a limit as h goes to 0 of the function where you plug in x plus h for all the x's. But notice there are no x's in a constant function. So f of x plus h is simply that constant, and then minus f of x is also simply that constant, all over h. Of course, k minus k is 0. So we're doing a limit as h goes to 0 of a constant function 0, and that just gives us 0 back. This gives us a quick formula that if ever you're differentiating a constant, you can just get 0. You do not need to go through this process every time. Okay, let's apply these shortcuts to some examples here. Here the independent variable is x. Notice there is no x in this function, it's just a constant 8. So this derivative is 0. In this next case, we're differentiating with respect to x, and there is an x here. So this is a linear function. When you graph y equals x, you get a line with slope 1, because 1 is the coefficient of x. So the derivative of x with respect to x is simply 1. In the next example, again, we're differentiating with respect to x, but this time I have a different letter. Now, unless otherwise specified, then we will assume that that different letter a is constant. So if you differentiate a constant, you will get 0. Now, the next example, we're switching the independent variable to y. This means that when graphing, y would be the horizontal axis, and the vertical axis would be some other letter. We're also differentiating the function y with respect to y. Well, this has the form my plus b, where m and b are constants. In fact, b would be 0 and m would be 1. So once again, this would be a graph of a line, again with slope 1. Its derivative is 1. Basically, if you differentiate a variable, such as y, with respect to that same letter, you're going to get 1 always. So the derivative of x with respect to x is 1. The derivative of z with respect to z would be 1, etc. Here we have differentiating with respect to y, and we have a different letter in here. So again, assume that different letter is some sort of constant. And when you differentiate a constant, you will always get 0. It doesn't matter the independent variable. Okay, let's look at these examples. Differentiating with respect to x, here's our x. This function is the equation of a line with slope 3, because it has our structure mx plus b, where m is 3, doesn't matter what the b is, and the derivative of any line is going to be the slope of that line, so we'll just get 3. This next function is a line with slope -5, differentiating with respect to x. So here's our independent variable. This has the form mx plus b, where m is -5 and b is +4. So we get the slope of this line, which is -5. Okay, a derivative with respect to x again. Here's our x. But here's a different letter. That different letter we will assume is a constant. And then we have an x divided by 2. That's the same thing as 1/2 times x. So we could rewrite this as the derivative with respect to x of 1/2 of x plus some constant b. Doesn't matter what b is, this equation would give us a line with slope 1/2. So the derivative of this line is 1/2. In our last example on this page, we're differentiating now with respect to y. So here's our independent variable y. There's 2 other letters in here, a and b, that we will assume are constants. So using y as the independent variable, this equation would produce a graph that's a line, and b would be the slope, because that is the coefficient of the independent variable. So the derivative of this function would just be b. Okay, let's go to the next page. Let's create some more shortcuts. Use the limit definition of derivative to find the following derivatives. We have the derivative of a power function x squared and then x cubed, and then we're going to generalize to x to the n. Focusing on x squared, this would be the limit as h goes to 0 of, and then rewrite this, except substitute x plus h in for x. So we have x plus h as the base, that's being squared, and then minus, and now just put the function x squared all over h. I'm going to FOIL this. Make sure you just don't say x squared plus h squared. The power does not distribute. You have to write x plus h times itself and then FOIL. That would give me x squared plus 2xh plus h squared, and of course we have minus x squared all over h. Now notice that x squared and negative x squared will cancel. So that takes us to limit as h goes to 0 of 2xh plus h squared all over h. Now we can factor out in h and cancel with the denominator, giving me the limit as h goes to 0 of 2x plus h, and then we can plug in 0 now finally into this remaining h, leaving me a2x. Let's look at x cubed. This will be the limit as h goes to 0 of, replace x with x plus h, so we would have x plus h as the base, and that's being cubed. Minus in the original function is x cubed all over h. Now to cube x plus h means you would need to write x plus h 3 times, and then FOIL 2 of them, and then distribute again. We've done this in prior lectures. I'll just put the result of doing this process. You would get x cubed plus 3x squared h plus 3xh squared plus h cubed. I'll leave it to you to verify that. And then we have minus x cubed all over h. And of course, we're doing a limit as h tends to 0. Right, notice x cubed and negative x cubed cancel. So you have a 3x squared h plus 3xh squared plus h cubed all over an h. Notice we have h's in all 3 terms now. We can factor an h out. So factor an h out and simplify with the denominator. Gives me 3x squared, no h's in that term, plus 3xh, still an h there, plus h squared, still h is there. And now all these remaining h's are going to shrink to 0. So you can substitute 0 in for those h's. So our final result is simply 3x squared. Now notice a pattern in both of these. Beginning with x squared, the power 2 is now a coefficient, and the new power that's on this x is an implied 1, which is one number less than this power 2 that we began with. Notice in the case of x cubed, this 3 and the original power 3 match, and this new power is 1 power less. It turns out this pattern will continue. I won't take the time to prove this statement for all cases of all powers, but it turns out that when you differentiate with respect to x, a power function, x to the n, again where n is just some constant, it could be any constant. It could be positive, negative, fractions, 0, irrational numbers. The derivative of x to the n will always produce that power times x to the, and then the new power will be 1 number less. This is a rule now that you can just memorize. Let's apply it to some of these examples. Here, a derivative with respect to x. We have an x to a constant. So the derivative of this power function will be equal to, this power 8 will become a coefficient, and then we repeat x, and then the new power is 1 number less, which would be a 7. Here we have a derivative with respect to z, and we have a z squared. So we get to use the power rule with z as the independent variable. The 2 will drop down, the z will repeat, And z's and 2's can look alike. To avoid confusion, I recommend you cross your z's. And then the new power on that z would be one number less than 2, which is a 1, which you don't need to bother writing. So we could just say 2z. Now on the last page, we talked about how the derivative with respect to x of just x ought to give us 1, because this function, when graphed, is a line with slope 1. But I can also use the power rule to confirm this, because there's implied power here. So if I think power rule, that 1 will drop down as a coefficient, the x will repeat, and we'll get a new power that's 1 less than 1, which is 0. But x to the 0 is also just 1. So in the end, we get just 1, showing that the two different rules, the two different ways to think about this, do not contradict each other. Now, derivative with respect to w of w to the 3.6, that power will become a coefficient, the w will repeat, and then the new power will be one number less than 3.6, which is 2.6. Okay, let's look at these examples. So derivative with respect to u, and there is a u involved, but it's 1 divided by u. So the trick here will be to express this function as a power of u. So we're going to do a derivative with respect to u of, and I'm going to rewrite 1 over u as u to the negative 1. And now we have u raised to a power, and I can employ the power rule. The derivative will be the negative 1 will become a coefficient times u, and then we do one number less than negative 1. So negative 1 minus 1 takes us to negative 2. And then, of course, I can rewrite this as negative 1 over u squared. Now notice in my notation, the differential operator I continue to write in my second step because I had not yet calculated a derivative. The purpose of the second step was simply to rewrite the function in a different way so that I can employ a power rule. And as soon as I actually employ differentiation rules and write down the derivative, which was done in this step, this is the step where we can finally drop the differential operator. Okay, similarly in this example, we have the derivative with respect to y of the square root of y. The trick here will be to express the square root as a power. So I'm going to rewrite this function as y to the 1/2. And I have not yet done a derivative, so I'm going to keep the differential operator ddy in front of this. And now I'm going to use a derivative rule and calculate the derivative, so I don't need to write the operator in this next step. So that 1/2 power will become a coefficient, and then we repeat y, and then the new power is going to be one number less than 1/2. Do this calculation in your head, or you can write it down. 1/2 minus 1, what does that produce? Get a common denominator, 1 is 2 over 2. 1 minus 2 is negative 1, so 1/2 minus 1 produces negative 1/2. And then let's take a moment and rewrite this in different ways. This negative power can push that y to the denominator to join the 2 and have a positive 1/2 power. And then a positive 1/2 power means to do a square root of that y. The derivative of the square root shows up so often that it might be worth just memorizing this result. Okay, in this next example, x is the independent variable. We have an x here. We're going to take a moment and express this function as x to some power. I see we have a cube root of x squared. A cube root as a power is a 1/3 power, so I could write it this way. Then you can multiply 2 1/3 and get 2/3, but that's still in a denominator, so I'm going to move it up to the numerator by using a negative power. So we're going to find the derivative of x to the negative 2/3. And now I can employ the power rule. So I don't need to write the ddx this time. The negative 2/3 will become a coefficient. And then we have to do a new power on x that's 1 less than negative 2/3. So either do this in your head or write it down. We're going to subtract 1 from negative 2/3. Well, that's like subtracting 3/3 from negative 2/3. And negative 2 minus 3 is negative 5. So my new power is negative 5/3, which I can rewrite negative 2 over 3x to the positive 5/3. And then if I wanted, I can rewrite that as negative 2 over 3 times the cube root of x to the 5th. You want to be comfortable working with these negative fraction powers and interpreting them in multiple ways. Okay, and there is the power rule being used in a variety of situations. Let's go now on to the next page. Here we have constant times function rule. So differentiating with respect to x, we have some sort of unknown function here, but then a k constant multiplying to it. Let's use the limit definition to get started. So if you have a constant times a function, and you're differentiating, you're going to get a limit as h goes to 0. The first part of our formula is replace all the x's with x plus h. So we'd have a constant times f of x plus h, and then minus the original function, which is just constant times f of x all over h. Now, since we don't know what the function is, it's not specified, the best I can do here is factor that k out. There's a k here and a k here in a difference, so I can factor it out. And I can factor out of the entire limit. So I can write this instead as k times the limit as h goes to 0 of just f of x plus h minus f of x all over h. And whatever f is, this expression in the brackets here is the representation of its derivative. So basically we get constant times and then the derivative of f, which is f prime of x. So in summary, the derivative of a constant times a function is simply that same constant, but times the derivative of the function f. So this becomes a rule that you really ought to memorize moving forward. Let's apply it in some of these examples. Is the derivative with respect to x of 3x to the fifth. So 3 is like some constant, and then x to the fifth is some function. So applying this rule, I know I'm going to get 3 will stay, and I now just have to differentiate the function next to it. So 3 times the derivative of x to the fifth. Well, x to the fifth is a power function. Its derivative is 5x to the 4, and because I've done a derivative now, the d dx can disappear. And then I can simplify this. 3 times 5 we can calculate is 15, and then times x to the 4. So basically, if you're differentiating a number 3 times a power function, this 5 will multiply to this 3, making this 15, and then the new power will be 1 less than it used to be, so dropping from 5 to 4. All right, this middle case, differentiating with respect to u, and there's our independent variable u there. I have a negative 7 over u squared. You're going to want to rewrite this before you differentiate. So we have the derivative with respect to u of, I'm going to move that u up with a negative power, so we have negative 7 times u to the minus 2. This is a constant times a function. So we can begin by ignoring the minus 7 and moving that differential operator to operate on just the u to the minus 2. We're going to use the power rule there. The negative 2 drops down, the u repeats, and then my new power is 1 less than negative 2. Make sure you don't think 2 minus 1 and get 1 and then say negative 1. You want to do negative 2 minus 1, which is negative 3. And then I can simplify this. The negative 7 and the negative 2 can multiply, and then the u to the minus 3 will push that u to the denominator with a positive 3 power. So I get positive 14 over u cubed. Okay, in this last example, differentiate with respect to y, so there's my independent variable there. I'm going to reinterpret division by 5 as multiplication by 1/5. We have a 1/5 times the square root of y. And I like thinking of it this way because we have a constant times a function. So the 1/5 can be ignored for the moment, and we just have to now differentiate the square root of y, which I'm going to rewrite as y to the 1/2. So I'm going to use the power rule, so the d dy goes away now. The 1/2 drops down as a coefficient. Then we have y, and then one number less than 1/2. 1/2 minus 1 produces negative 1/2. That negative power pushes that y to the denominator with a positive 1/2 power. And now I can simplify all of this. The 1/5 times the 1/2, that makes a 10 coefficient in the denominator. And then the y to the 1/2 is square root of y. Now earlier I said that you could just memorize the square root of y. And so from this point here, I could have just said this will be 1/5, and then the derivative of the square root of y memorized is 1 over 2 rad y, changed to 1 over 10 rad y. Okay, let's go on to the next page. Okay, the sum difference rule. If you differentiate some function plus or minus some other function, it turns out that you can differentiate these functions separately, giving you f prime of x, and then plus or minus, this sign would match whatever sign is there, and then differentiate the g function separately. We'll leave off the proof of this, but it's quite easy to show. So another rule to eventually memorize, find the following derivatives. So differentiating with respect to z, and notice we do have a linear function here of z. So this is a line with slope negative 5. So I know the answer should become negative 5. But let me use the rules that we've been developing to also arrive at the same result to show that we don't get any contradictions. So this is a difference of two functions, and I'll switch to primes. So we can differentiate the 4 separately, then minus, and then differentiate the 5z separately. This is a constant times a function, so I can ignore that 5 and just differentiate the z separately. So now we have it set up. Differentiating the 4 gives us 0, minus 5, and then differentiating z with respect to z gives you 1. So in the end, we get 0 minus 5, or negative 5. The next example, we have multiple terms. X is the independent variable. 3 total terms a term, a term, and a term that are being added and subtracted together. The rule on this page allows us to differentiate term by term when the terms are being added and subtracted together. So we can look at the 3x to the fifth as one function and differentiate it, and then plus. This middle term I'm going to rewrite as 5 halves times x to the 1/2, and then differentiate the middle term, and then minus, and then we can differentiate the third term all separately. I can use constant times function rules, so I can pull the 3 out and then only differentiate the x to the fifth. In this middle piece, I can ignore the 5 halves and only differentiate the x to the 1/2, and then over here, I'm just going to differentiate 1. So now I am prepped to actually do the 3 derivatives. The 3 will stay. Derivative of x to the fifth using power rule is 5x to the 4, plus the 5 halves will stay. The derivative of x to the 1/2 is 1/2 x to the negative 1/2, and then minus, and the derivative of 1 is 0. So you wind up getting 15x to the 4th. 5 halves times 1/2 is 5/4, and then that negative power pushes the x down with the 4 to a positive 1/2 power, which you could just rewrite as a square root of x, and then minus 0 we don't need to write, and we are done. Okay, next page. Find the following derivatives. Here we have 3 slightly more complicated functions. In this first case, we have a function, but then times a second function. Later, we're going to learn something called the product rule that we can use here. But for now, we do not have a rule for differentiating a product, but we do have a rule for differentiating a sum or difference. So the thing you're going to want to do here to begin is to turn this product into a difference by distributing. So we're going to have the derivative with respect to y of instead y to the 4th minus 2y. And now we have a difference. So I can differentiate y to the 4th as one term, and then minus the constant 2 times, and then we can differentiate the y separately. Using power rule, the derivative of y to the 4th is 4y cubed, minus 2 times, and the derivative of y is just 1. So our final result, 4y cubed minus 2. Notice I'm switching from this differential operator, which establishes what the independent variable is very clearly, to a more lazy prime sign, which you should feel comfortable doing as long as it's clear what the independent variable is. Okay, it's middle case. The numerator is a product of 2 functions, and then we have divided by a third function. Later, we will learn something called the quotient rule for how to differentiate a function divided by a function. But for now, we do not know how to do that. So our only option here is to somehow express this as a sum or difference. We'll do this in a few steps of algebra. I'll begin by taking this 2 rad x and distributing it across these parentheses. So I'll have the derivative d dx of, we'll have 2 rad x times x, and then minus 6 rad x. And this is all over x. Now this radical x is x to the 1/2 power. Same for this one. Now you may recall the rule that if you have something like x squared times x cubed, the rule of exponents is that you would add these powers. So in general, if you have x to the a times x to the b, you would get x to the a plus b. We're going to have to use that to simplify this product, because this x is really an x to the 1, and so I can add these powers to make a new power on x. 1/2 plus 1 is 1/2 plus 2 halves, which is 3 halves. So my new power on x is 3 halves, and then the rest. Now we're going to use another rule. If ever you have a divided by b plus c divided by b, if they have the same denominator, you can combine the numerators and keep that same denominator. We'll use this rule backwards. This x can be divided under this term and then under this term separately. You can split a denominator. So that gives me the derivative of 2x to the 3 halves over x, and then minus 6x to the 1/2 over x. Now another rule of exponents. If you have something like x to the 5th divided by x squared, it's like having 5x's multiplied divided by 2x's multiplied. You get cancellation of 2 of the x's and 2 of the x's, leaving x cubed. In other words, if you have x to the a divided by x to the b, you can combine this into a single power of x by doing a minus b. Well, over here, you have an x to the 1 and another x to the 1. So I can take this power and subtract that power to get a new power for x. So this becomes the derivative of 3 halves minus 1. That's 3 halves minus 2 halves. That's going to take us back to 1/2. So we have x to the positive 1/2, and then minus 6 times. Now I do 1/2 minus 1. That's 1/2 minus 2 halves. That's negative 1/2. Now up to this point, I have not been doing any derivative rules, just algebraic manipulation in order to prep the function so that I can now easily employ derivative rules. So I can differentiate this difference term by term. The 2 I can ignore, and we're going to differentiate the x to the 1/2, minus, and then the 6 I can ignore, but then differentiate the x to the negative 1/2. Now this first one is just square root of x. I'm going to use my memorized derivative of it, which is 1 over 2 square root of x. So we have 2 times 1 over 2 square root of x, and then minus 6 times. Now here I'll use the power rule, so the negative 1/2 will become a coefficient, x will repeat, and then we have to do negative 1/2 minus 1. That'll be negative 1/2 minus 2/2, which is negative 3/2. And now I've finally completed the derivative. Now I just have to simplify my answer. The 2's will cancel in this first fraction, so just 1 over square root of x. Negative 6 times negative 1/2 will be positive 3. And then this x to the negative 3/2 will move that x to a denominator and put a positive 3/2 power on it, which I could rewrite now as 3 over the square root of x cubed. And here's a good finalized answer. In this final case, here I have a function raised to a power. There will be a rule that we will learn later on how to address the situation. But for now, I do not know how to differentiate a function raised to a power. So I'm going to have to use some algebra to FOIL and then differentiate term by term. Now we are doing a derivative with respect to t. Here's my t. This other letter a we're going to assume is a constant. So we're going to do a derivative with respect to t, and then we'll have a 3t plus a times another 3t plus a. 3t times 3t is 9t squared plus 3at plus another 3at plus a squared. The two middle terms are similar, so I can add them and get 6at, and now I can differentiate term by term. So we're going to have 9 times the derivative of t squared. 6a is a constant because a is a constant. So 6a times the derivative of t. And then here a squared is just a constant because a is, and we'll differentiate that constant. So we're going to have 9 times power rule gives 2t plus 6a times the derivative of t with respect to t is 1 plus, and then a is a constant, a squared is a constant, and the derivative of a constant is 0. So in the end I get 18t plus 6a. So all three of these examples demonstrated several steps of algebraic manipulation prior to being able to apply the derivative rules that we've learned so far. Be mindful of notation about when the prime signs or the differential operators can safely disappear in your work. And the last page. Find the following derivatives. There's 3 quick derivatives up top. X is the independent variable. There's our x. When you're dividing by a constant, the best way to think about this is to pull that division by 6 and interpret as a 1/6 times an x. This is just a linear function with the slope 1/6. The answer will be 1/6. Now is the reciprocal, 6 divided by x. In this case, you want to reinterpret this as 6 times and then bring the x up with a negative power and then differentiate this using constant times function rule and power rule. Well, the 6 will stay, and then differentiate x to the minus 1 gives me negative x, and the new power will drop to negative 2. And this is the derivative. Notice the prime sign has disappeared. And then, of course, this can be rewritten as negative 6 over x squared. In this third case, we have the 6 and the x both in the denominator. The best way to think about this is to pull this apart as 1/6 times 1 over x and differentiate that, which means I can ignore the 1/6 and rewrite the 1 over x as x to the minus 1 and find that derivative. So the 1/6 stays, and the derivative of x to the minus 1 will be negative x, and the new power will be minus 2. And then simplifying that, in the end we get negative 1 over 6x squared. In our last set of instructions, find where the graph of y equals 6 over x has a tangent line that is parallel to the line 4x plus 2y equals 3. Give the equation of such a tangent line. Well, notice that this function right here is our middle case, and that graph is shown in the image here. Now we're given a line over here, 4x plus 2y equals 3, and we're going to want to know what its slope is. So the easiest way to do that is to put this in slope-intercept form by solving for y. I'm going to subtract 4x to the other side, so we have 2y is equal to 3 minus 4x, and then divide everything by 2. And I'll put the x term first. So we have negative 4x divided by 2 is negative 2x, and then plus 3 divided by 2. So the slope of this line is negative 2. The y-coordinate, the y-intercept is 3/2, so 0, 3/2 is the y-intercept. So we can graph it in our image. Begin with the y-intercept at 0, 3/2. 3/2 is 1.5. And then we have a slope of negative 2. So if I go right 1, I would have to go down 2. 1, 2, giving me this blue line, y equals negative 2x plus 3/2. Now I want to find points on this curve where the tangent line is parallel to this blue line. And when two lines are parallel, it means they have the same slope. So a bad choice would be to pick this location, because when I imagine the tangent line there, the orange and blue lines are not parallel. So imagine you can move this line around without changing its slope, and then try to figure out where you would get tangent C. And notice we could also get tangent C over here on this part of the curve somewhere. That leads me to believe that I'm looking for two different points, one around here somewhere, and a second one around here somewhere. Well, how do we go about finding these points? Well, we know that if our function that's graphed in black here is 6 over x, we know that its derivative, which we just computed above, will be negative 6 over x squared. What we want to do is figure out what input you would need to plug in here so that the output is the same slope as the blue line. This is what we're trying to figure out. So we're going to set f prime of x equal to the desired slope, creating an equation that I can solve for x. Well, f prime of x is negative 6 over x squared, and the desired slope is negative 2. And we can solve this equation for x. I'll begin by multiplying both sides by x squared. Well, x squared times this fraction, the x squares will cancel, leaving minus 6 on that side of the equal sign. And now multiply these two expressions, just giving me negative 2x squared. Now I'm going to divide both sides by negative 2. So I get 3 is equal to x squared. And then solving for x, take the square root of both sides. Now you're going to have to say x is plus or minus the square root of 3. Square root of 3 is about 1.7. So these are the two x coordinates of these orange points in our graph. This one is square root of 3, comma, some y coordinate. And this one is negative square root of 3, comma, some y coordinate. Well, how do you get the y coordinates? You would plug this x coordinate into this function to get the y coordinate. So 6 divided by square root of 3 would be the y coordinate of this point, and negative 6 divided by square root of 3 would be the y coordinate of that point. Let's call this line 1 and this other one line 2. The instructions ask us to only find one such tangent line. So let's find the equation for line 1. So we know that x is the square root of 3. The y coordinate will be found by plugging square root of 3 into the function, which we've already done, getting 6 over square root of 3. And then the slope of the tangent line will be f prime of square root of 3. So you'd plug square root of 3 into this function, giving me negative 6 over square root of 3 squared. Well, square the square root of 3 gives me 3, and negative 6 over 3 is negative 2. Well, that's no surprise. We already knew that we wanted the slope to be negative 2 so that it matched the slope of the blue line. To find the equation of the tangent line for line 1, we're going to do y minus the y coordinate, which is y minus f of square root of 3, is equal to the slope of the tangent line, which is f prime of square root of 3, times x minus the x coordinate. So specifically, that gives me y minus 6 over rad 3 is equal to the slope, which is negative 2, times x minus square root of 3. I'm going to go ahead and isolate y, distribute the negative 2, gives me negative 2x plus 2 rad 3, and then we'll add the 6 over rad 3 to the other side, and we will call this done. Let's confirm this one with some technology. Okay, we have the graph of f of x equals 6 over x. Here's the graph of the line that was given to us. I'm going to type in the answer that we got. Y equals negative 2x plus 2 square root of 3 plus 6 over the square root of 3. And sure enough, we get an orange line that's tangent to the curve, and the orange and blue lines are parallel to each other. Let me hide this line. You can also do something very clever and interesting with Desmos. We found that there was a tangent line when x was negative 3. So I'm going to create a new variable a and say that it's equal to the square root of 3. And then my line was found by doing y minus, and then the y coordinate was f of that value a. So we're plugging a, which is square root of 3, into the f function, which I defined up here in line 1. F of x equals 6 over x. And we want this to be equal to the slope, which is f prime of this value a, and then multiply that slope by x minus this x value a. And notice that I never even had to actually find an answer. I just had to know that we have a tangent line when x is square root of 3, and I can type this in to make that tangent line. I'm also interested in seeing the point of tangent C, so I'm going to make a new line that's a comma f of a as a point, make it match color, and turn on the label. Now what's interesting here is that I can change a to other values now and get different tangent lines. In fact, I can create a slider. Let a vary from negative 10 to 10. Let's just do a step size of 0.1 for now. And I create a slider that I can hit play on and see different tangent lines as a varies to different numbers. Okay, and this concludes our lesson on basic derivative rules.